For every grain of sand on all the beaches of all the lakes, seas, and oceans on Earth, there are about 10 stars in the observable universe. For every grain of sand. That is roughly 10 to the 24 stars, or an incomprehensible 1 septillion stars, and some astronomers think that that is a lowball estimate. For each of these stars, there is on average at least one planet surrounding it. About 1 in 5 sun-like stars have an Earth-sized planet in the habitable zone. This means that in the Milky Way alone, there are around 11 billion potentially habitable worlds that are very similar to the Earth. Given this astronomical number of planets with the potential to harbor life, surely we are not alone in the universe, right? Enter the Fermi paradox. Named after Italian-American physicist Enrico Fermi, the Fermi paradox is the apparent contradiction between the lack of evidence for extraterrestrial civilization and the varyingly high estimates for their likelihood. Fermi believed that any civilization with a modest amount of rocket technology and an immodest amount of imperial incentive could rapidly colonize the entire galaxy, and that within 10 million years, every star system could be brought under its control. Seeing as that we're not under the control of an evil ET empire, and that the universe is already 3.6 billion years old, where are all the aliens? Given the massive scale of the observable universe, scientists have taken many different approaches to quantifying the total number of alien civilizations. One of the most famous attempts at this was developed in 1961 by SETI co-founder Frank Drake. Drake's famed equation estimates the number of civilizations in the galaxy by measuring detectable electromagnetic emissions using specific variables related to habitability. The results from the first use of the equation estimate somewhere between 1,000 and 100 million alien civilizations just in the Milky Way. However, 4 of the variables in the equation are completely unknown and are thus just estimates, which astronomers rarely agree upon. Those who criticize Drake's equation cite this shortcoming, stating that while the equation was a good first step in thinking about how we should look for alien life, it should not be taken as a hard count. Here are a few of the most interesting or commonly accepted conclusions from the Fermi paradox, in no particular order. Rare Earth hypothesis. The rare Earth hypothesis states that the probability of life forming on its own, abiogenesis, is incredibly improbable, and that the unique formation of our solar system is the reason why life was permitted to exist here. Number 2. We need more time to look. Space is really big, and the distance from us to other star systems makes it really hard to send and receive messages. The speed of light is fast, but not fast enough to be able to broadcast to the entirety of the Milky Way. Number 3. Wrong channel. Maybe we aren't looking for alien life in the right way at all. Sending radio waves makes sense to us humans, but it might not make any sense or even be understood as a message by other alien species. Since the advent of the radio at the end of the 19th century, we've been broadcasting our existence to the galaxy at large and have made it past a few stars in our neighborhood. However, radio waves are just another form of light, and as such, may not even be capable of being heard by aliens. Just as we bask in the beautiful colors of the rainbow, alien life may do the same with the top hits of the 1920s. Number 4. Zoo Lab Hypothesis. Both of these hypothesize that an advanced alien civilization have hidden themselves away from us in order to observe our species. The zoo hypothesis, as its name infers, places us inside the zoo and aliens on the outside, keeping their distance to allow us to evolve and exist without any outside interference. The lab hypothesis argues that perhaps these aliens regularly intervene with our proceedings and effectively treat us as their lab rats or popular entertainment. And finally, we have the Great Filter. This is the scary one. The Great Filter hypothesizes that all life forms across the universe encounter a seemingly insurmountable obstacle that it is either eradicated by or successfully passes. This filter would explain the apparent rarity of extraterrestrial life in the universe. Many hypothesize that our Great Filter moment was either the creation of the very first cell or the transformation of the simple prokaryotic cell to the more sophisticated eukaryotic cell. What these hypotheses suggest is that we've already passed it, However, there is always the lingering possibility that this filter is around the corner, and that humankind, like all other intelligent species before us, will perish at the hands of it. Many suspect that the Great Filter does lie ahead of us and will most likely come as the result of unabridged technological advances like hyperintelligent AI or mass nuclear war. If we have truly passed the Great Filter, then we could be the only intelligent, advanced civilization in the entire empty universe. Thank you for watching, and I hope you enjoyed.